So in this packet, we're talking about rate and accumulation. And if you think about it, we've talked about rate a lot in our class. A rate is a derivative, right? Miles per hour, calories per minute. Rates are changes in time a lot of times. So number 1 says the flow of oil in barrels per hour through a pipeline on July 9th is given by the graph shown above. Of the following, which best approximates the total number of barrels of oil that passed through the pipeline that day? So we're supposed to find total barrels. We're supposed to find all of the barrels. We're given barrels per hour and hours. So this is a graph of the derivative. This is a graph of the rate. And if you remember, when we find area under a curve, isn't that an integral? When you do an integral, you're really finding area under a curve. So if we find area under this curve, and this is a rate, wouldn't it be finding like this box, how much area is in this box, which is 6 by 100? So this would be about 600 units. Is it exact? No, but it's about. And then this is a full box, so there's another 600. Here's another box. Here's about a box. So all of these would be about 600 because this distance is 6, 6, 6, and the height is 100. And then what I did is I said, okay, this part up here looks like it's probably almost a full box. If I take this piece and plug it here, take this piece and plug it here, that looks like another whole box of 600. So there are 5 boxes of about 600. And look, it's 6 hours times 100 barrels per hour. Doesn't that get us back to barrels? And that would have been 3,000. 6 times 5 is 30. So since we have 600 times 5, that would be 3,000. Number 2 is actually going to be a calculator active problem. It says insects destroyed a crop at a rate of 100 e to the negative 0.1 t, all divided by 2 minus e to the negative 3 t, tons per day. There are so many key phrases just in that first sentence. Rate, tons per day. So I hope that you look at this and you think, oh, yeah, I am given a derivative. That is a derivative. To the nearest ton, find tons. We're given tons per day. We want to find tons. How many tons did the insects destroy on the time interval 7 to 14? Well, if we take the integral of a rate, aren't we going to be back to tons? If we take the integral of this, which is tons per day, over the interval from 7 to 14, when we figure this out, we have these units, which was tons per day, times our boundaries units, which are days. T is measured in days. T to 7 to 14 days. We're left with tons. So in our calculator, we would just put this in our calculator and find the value, and we end up with 124 point something, so A, to the nearest ton. Number 3, the rate of change of the altitude of a hot air balloon is given by R of T. Okay, come on, write again. The rate of change of altitude. R of T is a derivative for 0 to 8. Which of the following expressions gives the change in the altitude of the balloon during the time the altitude is decreasing? We want to know when the altitude is decreasing. How can we find, this is the rate of altitude, so that's the derivative of altitude. The derivative tells us increasing and decreasing, right? So we need to find the where the altitude is decreasing. And again, I used my graphing calculator. You should try this. I put this in my calculator, R of t. I changed my window to go from 0 to 8 for x, and my y values, I went from -1 to 1, because all I care about is where is it above the x-axis and where is it below. So when this graphed from 0 to 8, when I looked at the graph, it was above the x-axis, then below, then above, and there were 2 critical points. I used my graphing calculator. I went to F5, and I found the zeros, and it was 1.572 to 3.514, and it's decreasing between those. So that allowed me to cross off B, C, and E. That's when the altitude is decreasing. Now, we want the change in altitude, okay? Think of change in position, right? Change in altitude, change in position. So change in position is the integral of velocity. Now think back, I know I wasn't here when we did that, but isn't the antiderivative of velocity s, and then we evaluate from a to b? So that would be the change in position, s of b minus s of a. That's how much we moved. We also called that the displacement. So the change in altitude is going to be the integral of the derivative of altitude. Well, the rate of change was given by r. This was a derivative. So we just want r of t, not r prime. So we want letter A. Next, I'm going to the first FRQ, and we're going to talk about this one together. This right here tells us what the average score was in the nation on this exam question. It says, at an intersection in Thomasville, Oregon, cars turned left at a rate of L of t, cars per hour, over the time interval 0 to 18 hours. The graph of L of t is shown above. Okay, so a couple things should jump out at you. Rate, so this is a graph of the derivative. This is also a calculator problem, so the first thing we should do is go to our calculator and plug this in for y1. Put your L of t in for y1, and then you're also going to change your window. Change your window to match the graph that is shown right here. Change your window to match the graph that's shown right here. Okay, so when I go to my calculator, I put my window 0 to 18 for x and 0 to 250 for y. And when I hit graph, I should be seeing the same graph that's on my paper. Now it's all in there. Keep in mind, this is a graph of the derivative. So letter A says, to the nearest whole number, find the total number of cars. This L of t is cars per hour. Find the total number of cars turning left over the time interval 0 to 18 hours. So to find total cars, we're going to take the integral of L of t from 0 to 18. This is cars per hour. This is hours. So when we find this, we end up with cars. Again, this is all calculator active. So you just use your calculator, put it into your calculator, second 7, y1, parenthesis x, close your parentheses, comma x, comma 0, comma 18. And it comes out to, because it said to the nearest whole number, I wrote 1,658 cars. You would get 1 point for the integral, and you would get 1 point for the 1658 cars. Okay, letter B. Traffic engineers will consider turn restrictions when L of t is greater than or equal to 150 cars per hour. Find all values of t for which L of t is greater than or equal to 150 and compute the average value of L over this time interval. Indicate units of measure. Okay, so we want to look at when L of t is greater than or equal to 150. On my paper, I drew this line. That's where L of t would be greater than 150. That's the line 150. Do you agree that this intersects twice? So the first thing that I would do is go to my calculator, put 150 in for y2, and I would look at where they intersect. So I'd go back to my graph, I would do F5, and I would find those intersections. And then I like to store them, remember? So on my paper, I wrote let A equal 12.42831, and let B equal 16.12166. I found those by finding the intersection. So they'll consider turn intervals if L of t is greater than or equal to 150 cars per hour. So we're finding values of t where it's greater than. So the interval is going to be the interval from A to B. Okay, that's part 1 of it, finding the interval. So there's my interval. Because I said let A equal and B equal, I can just use the interval from A to B. Now it says compute the average value of L over this time interval. Average value is 1 over B minus A times the integral from A to B of L of t dt. I don't even have to put my numbers in there because I already said let A equal and B equal. So this is the formula, and I can just leave it like that. And then I have my calculator, which will do the work for me. So I would put in I would go home and I would say 1 divided by parenthesis B minus A, blah, blah, blah. Then I get 199.426. Now, it says to make sure you have appropriate units. So let's take this one step at a time. Didn't the integral in part A, didn't this integral right here give us cars back in part A, right? Because we had cars per hour times hour, cars per hour times hours. But we have this 1 over B minus A. So what is this? What's B minus A talking about? These are hours. So this is 1 over hours. So this 199.426 is actually back to cars per hour. It's the average number of cars that turned left every hour from time A to time B. That was worth 3 points on the actual AP exam. 1 point if you had the correct interval from A to B. 1 point if you had this interval in blue set up correctly. And 1 point for the answer, but you also had to have the correct units. And I've had people in the past get it wrong because they put the wrong units. Make sure you analyze carefully. Traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight. Does this intersection require a traffic signal? Explain the reasoning that leads to your conclusion. Okay, so let's go back here. The product of the total cars turning left and the total cars going straight. Well, first of all, product is multiplying. So the cars turning left times the cars going straight would have to be greater than 200,000. Well, how do we find when the cars are turning left? We find when the cars are turning left by using the integral of L of t. And it says straight is every 2-hour time interval, 500 total cars go through the intersection. So straight is just going to be a flat rate of 500. So really what we're looking for here, is there a time interval when L of t, D of t is greater than 400? That's the question. So that's what we have to look for. And I would find two values. Well, don't you agree that the highest values occur somewhere here? And we already know that that intersection is 12.4 to 16.1. So let's use a 2-hour time interval there. So what I did is I said, okay, I'm going to try the integral from 13 to 15 of L of t dt. 13 to 15 gave me 431.931 when I put it in my calculator. And since 431.931, remember you always have to have 3 decimal places unless they tell you otherwise, is greater than 400. So, yes, a traffic signal is required. At this intersection. So a traffic interval, because we found a 2-hour time interval that worked, that's it. Now, did you have to use 13 to 15? Absolutely not. Maybe you tried 14 to 16 and that worked. You just needed to come up with some interval that's a 2-hour length that would have worked. Okay, I hope that helped clear up some confusion, and I hope that will help you start thinking about doing the rest of these problems for homework tonight. So you're going to finish the multiple choice. I believe there's 3 of them. And there are 2 FRQs that I would like you to try. Before I send you on your way, notice that number 2 here has 2 values. They have tide removing sand at a rate of R, and they have pumping station adding sand at a rate modeled by S. So both of these are rates, keep that in mind. One is taking sand away, and the other one is adding sand. So keep that in mind when you do this problem. I really want you thinking about this on your own for these last 2 FRQs as well as these multiple choice. Let's see if any of this helped and makes a little bit more sense. Remember, our goal here by May 15th, I think it is for you to be getting 5-6 points on every FRQ. Of course, our goal is 9, but there's a lot of ways where you can mess up on these problems. So if you get a 5 or a 6 on every FRQ, we're doing really well.